Calculating the electric potential function. In electrostatics, only the infinite plane has a uniform electric field. All other fields are variable fields. So I'm going to break it down into uniform fields versus variable fields. So the first one I'm going to look at is work done by a uniform electric field. Suppose there are two large plates. Now, when you have this configuration of plates, you'll see that sometimes they'll say that they're capacitors. The electric field at the center is uniform. So if I set up my field here, I'm going to say that I have this parallel plate and this one right here. And so I don't look at the edges. I'm not interested in the edges. I'm only interested in the middle of the plates so that I can treat them as parallel plates. So let's say that the upper plate has a positive charge and the lower plate is negatively charged. So if they're infinite fields, then what I'm going to see here is that the positive plate has a field going like this everywhere. And then the negative plate has a field that looks like this. And so what you're seeing here is that above and below the plates, superposition says that they cancel. So now if I look at the net field inside, we see here that those two fields are adding up. So I'm going to get 2 of the infinite plate or the infinite plane field. So when I look at that, that's going to be 2 times eta over 2 epsilon. So therefore, that's the field inside there. So when I look at this field, since we're not really interested in anything else but a uniform field, before I forget, I'm going to say that this distance is the separation from the plate. Okay, so now here's I'm going to move this out of the way and I'm going to say that I have electric fields. So this is going to be my electric field. Here's another of the electric fields right here. And so now I'm going to look at charges. So to calculate a potential energy function, the test charge either moves with the field or against the field. So if I'm looking at the field here, let's talk about the first case here. So the first case I'm looking at is that I'm looking at motion with, I just want with to stand out, motion with the field. So I imagine that I have a positive charge here. And as a result, this charge is going to move and it's going to end up down here towards the negative plate. So I'm seeing this motion going in that direction. So I need to draw that exact same thing. So now here I can draw where I have a positive charge and it's going to move to right here. And its motion is in that direction. And I now have an electric field. That electric field is moving in, not moving, but it's pointed in the downward direction, the net field. So when I'm looking at this, there's going to be an electric force and there's going to be a displacement, and that displacement and the force are in the same direction. So what we say here is that the E field, the electric field, does positive work. And the reason why it does positive work, because of what we talked about last time, the force and the displacement are in the same direction. So according to this here, then the work of the electric field should be the electric force times the displacement, which will be d minus 0. So then I can write this out, but I know what the electric field is. And so therefore I can write in the electric field where this guy's then going to be Q eta over epsilon d. So now I have my work. So what does that work do? So that work does positive work. So then what's happening here is that this means the charge moves from high to low electrical potential energy states. Therefore, a decrease occurs in electrical potential energy. And that's not a surprise here because now I have the work of the electric field, and that's the negative of this guy. So if this is positive, that means that the potential energy is negative. So then this has to be minus Q eta epsilon times d. And this guy is negative, telling us that the charge is doing what? It's moving from a high energy state to a low energy state. Now we can do the same thing with our other situation. So now what we're doing is that we're looking at motion against the field. So now if I'm coming over here, what I'm imagining that I have a positive charge that's now going to move upwards this time. So you could see it's going to be moving against the field. We already stated multiple times that if you move with the field, there's a decrease in energy, and that's what we mean by the decrease in potential energy. So here we expect an increase in potential energy. So now in this situation, we now have a positive charge that's now moving up against the field. So once again, we have an electric field, and we already know that this is the low energy and this is the high energy state from the previous example. So now when I look at this thing, I'm seeing that now I have negative work that's going to be done because the displacement is upwards. Now, a little bit of care should be done here. The electric force cannot move this charge up above. So we should say this is that for a charge moving against the field, it can't be electrical in nature. And the reason why is that if I have a positive charge right here, the positive charge wants to stay closer to the negative plate than the positive plate. No electrical force is going to force that up. So what we have to have is that we have to have some other non-electrical force. So I'm going to say that this is an external force and this is non-electrical. So then we say here is that this work can only be done by a non-electrical force. Since there is external work being done to the system, there must be an increase in electrical potential energy. Once again, that is the charge moves from a low to a high energy state. So then we have to look at, there's two pictures. And the two pictures are here is that we clearly see that the external work is positive. So then that means here is that if I have work that's non-electrical, then that has to have a positive increase in the electrical potential energy. And we've already know what that is because that should be Q eta over epsilon D. However, we're also seeing here is that the work of the electric work, well, that still implies here that in this case, this electrical work is negative while the non-electrical work is positive. And that implies then that the potential energy will also be positive because of Newton's third law. So that is the cause of that increase in energy. Now let's go to the work done by a variable force. And what I'm going to focus on is that I'm going to focus on the point charge field because it's the easiest. So what we want to do here is calculate the electrical potential energy function for a point charge. And if you're outside the sphere, it acts the same. So to calculate the electric field is position dependent because we know that for a point, and remember what I said, if I talk about a sphere, but I have to be outside the surface, this is then given by 4 pi epsilon r squared divided by q. Now, I want to sketch this situation. So let's sketch the situation of a test charge moving towards a source charge, where I'm going to say both are positive. So here's my source. And because this is my source here, I'm going to call big Q to be the source charge. Now what I'm doing is that I'm going to take a little charge. Let's say it's this far out here. And my whole goal is to move the charge closer. And so when I'm looking at these charges, we typically talk about points in the field. So I'm going to say, I'm going to move this to point P. So typically the test charge starts at infinity and then moves all the way to point P. So now if I look at the electric field, it is very clear that the electric field has to be pointing away. And if I call this state one, I'm going to say that little q is the test charge. And that's what that guy is right there. So because it's a variable field, I know that I have to have, if I'm looking at the force of my hand here, then I'm going to have to integrate this, and it's going to move in this direction here. So I'm going from point 1 to point 2. So then I have to identify my locations here. So if I look at this, I'm going to say that the distance from here all the way to the center of the charge is R1. And the distance from point P to the center of the charge also is R2. So now that's my picture here. So let's go look at this. So now, calculating the work, I'm then going to see that I have an external force doing the work. So I'm going to say that this is the external work, and I'm going to define that as the work from 1 to 2. So we know that we have to overcome the force here due to the electric field. So then I'm going from 1 to 2, and I have F E dot ds. I know that the field here is related to the force by Q times the E field of a point. So if I start to put this all together here, note that the dot product between the electric field and the displacement vector are going to be in opposite direction. So I'm going to get a minus sign here, and I'm saying that this guy is the dot product. It's a consequence of the dot product. So now I am integrating from 1 to 2, and now I have the electric field. And then I have dr right here. So if I keep looking at this, and let's go through the integrals. So I'm going to factor out all of the constants. So then I'm going to get minus 4 pi epsilon over little q, big Q, and then I'm integrating dr r squared. And so when I compute this, what I'm going to get is that I'm going to get a minus sign from the integral, and in the end, 2 minuses gives me a plus, so then I get a result that looks like this. And this is R2 minus R1, and that has to be positive. So why is this positive? The reason why it's positive is that R1 is greater than R2, which then implies that 1 over R2 is then greater than 1 over R1. This shouldn't be a surprise, right? This is not a surprise. Because the work of the non-electrical force does positive work. So it's adding energy to the system. Now, but we're not, so if I look at this, then what I want to do here is that I want to let me say this, it is customary not to write the work done like this. So it is customary to rewrite this expression by setting R2 equal to R, and R1 is now the reference position, which I'll call just REF. So if I rewrite this, we then say that the work of 1 to 2, let me be careful here. No, that's not what I want to say. So then, because the work of the electric is in the opposite direction, this becomes the change in the potential energy. Now, let me be careful here, because now the work from 1 to 2 must be the opposite of the electrical. Ooh, not external, of the electrical here. That's where I'm getting that result right there. So when I write this, then this is going to be minus 4 pi epsilon into little q, big Q of 1 over R reference. And that's how we write that potential function. So now I can adjust the minus sign here. So then if I do a rewrite, we then say that the potential of a point charge as a function of R is then going to be the potential at R minus the potential of the reference point. And then this is what we call, then I just come in here and I rewrite the same expression. So we need to separate the language here a little bit. This right here is the work energy theorem. This right here is only the potential energy function. Even though it's part of the work energy theorem, it's different. So what I'm seeing here is that the negative work of the electric field, in other words, if we rewrite this, that's what I mean by the negative work causes an increase in potential energy.